Hello everyone, this is Wenchi Cheng from Xidian University, China. In recent years, natural disasters such as earthquakes, typhoons, and floods, also with COVID-19, frequently occurred. These natural disasters and hot events seriously threaten the safety of people's lives and properties, as well as the stability of the whole society. Meanwhile, emergency wireless communication, which is a prerequisite for efficient rescuing in post-disaster areas, should be paid much attention. However, also a number of advanced 5G and 6G potential technologies have been developed. How to directly use or revise them for emergency wireless communication is an interesting but very challenging problem. This challenge motivates us for the following works.
Here, I'm going to talk about recent years' studies on emergency wireless communications. The topic of this tutorial is Emergency Wireless Communications for Next Era: Challenges, Applications, and Future Trends. This is a collaborative work with Professor Zhang from the University of New South Wales, Australia. The tutorial mainly contains three parts. First, I'm going to talk about the background of emergency wireless communications. Especially in recent several years, the frequent natural disasters and hot events, along with the challenges caused by emergencies. Second, I'm going to talk about emergency wireless communications enabled technologies, including emergency wireless communications based complex channel model, UAVs enhanced emergency wireless communications, reconfigurable intelligent surface, empowered emergency wireless communications, through the Earth emergency wireless communications, as well as low latency, diverse quality of service guarantees in emergency wireless communications networks. Finally, future trends regarding intelligent emergency wireless communications are given. Okay, now let's start. For commonly well-known civil communications, there has been an ongoing effort to enhance performance available to end users. Once the industry reaches the corresponding level of data rates, higher targets are set again, driven by the everlasting demands of users. The first generation wireless communication mainly uses a completely analog modulation. The second generation wireless communications mainly builds on digital communications. The goal of the third generation wireless communications is to provide sufficient data rates for voice and mobile internet. The fourth generation wireless communications can provide broadband-like data rates for mobile devices, and the key technology to achieve it include MIMO and OFDM. The fifth generation wireless communications supports three kinds of scenarios like eMBB, MMTC, and URLLC. The sixth generation wireless communications is expected to achieve 1,000 times BPS higher than that of 5G. And the network delay is expected to be reduced from milliseconds to microseconds. Generally, although the first generation to the future, the sixth generation, wireless communications evolution goes well and very fast. The specific wireless communications technologies stick to emergency events are often just borrow the related technologies from techniques of severe wireless communications of each generation. However, different emergency events such as volcano, floods, earthquake, cyclone, along with new secondary disasters, requires continuous specific technology evolution. In the aspect of earthquake, the Chile earthquake occurred on September the 16th, 2015, lasted for a total of 3 minutes. The earthquake has affected nearly 1 million people. In view of destructions of power facilities and communications infrastructure, rescue crews have made great efforts and spent a lot of time in searching and rescuing. Despite the communication during rescue, it is also crucial to communicate with rescue crews without base station communication. In the aspect of volcano, satellite images captured the spectacular eruption of Tango volcano in 2022, with ash, steam, and gas rising like a giant mushroom above the South Pacific. Tsunami waves of about 80 centimeters crashed into Tanga's shoreline and crossed the Pacific, causing minor damage from New Zealand to Santa Cruz, California. Despite the message from Center Command, the rescue crews were unable to communicate because the submarine cable for communication across Tango was destroyed. On August 13, 2021, a magnitude 7.6 earthquake occurred in the South Sandwich Island, along with a huge tsunami. Rescue crews need to always pay attention to secondary disasters, and the destruction of base stations makes communications unavailable. Hurricane Harley made landfall on the Texas Gulf Coast August 25, 2018. A rain gorge near Highlands, Texas, registered 51.88 inches of rainfall, breaking the record of the continental U.S. At least 41 deaths has been reported. Over 30,000 people have taken refuge in shelters as dangerous flooding slowly recedes. Strong winds and heavy rain make rescue missions very challenging. 2021, the storm ran, which had initially packed winds of up to 260 kilometers per hour, with gusts over 300 kilometers per hour. Later moved west, bringing with it heavy rain and widespread flooding. Communication and power was out in several parts of the Philippines, making rescue efforts difficult. Actually, for natural disaster, the rescuing operations can be classified into three categories, as shown in this figure. First, airplanes or UAVs-based large-scale area detection and searching. Second, the ground-based rescuing for key areas. Third, underground or even underwater areas searching for trapped people. On the other hand, for hot events such as COVID-19, two cases are listed. First, with the help of the U.S. Department of Health and the U.S. National Guard, the Los Angeles Convention Center has been transformed into a mobile cabin hospital in 2020. Second, a 1,200 bed field hospital established in response to the need for additional hospital beds as a lower COVID-19 overwhelms New York City's existing medical infrastructure, opened on March 30, 2020 at the Jacob K. Jarvis Center. The requirements for communication bandwidth and delay has greatly increased in post-COVID-19 era. Wireless communication technologies are necessary to fight communication challenges, such as monitoring the spread of the virus, enabling healthcare automation, and facilitating online education and conference. Emergency technologies are playing a significant role in winning the fight against the pandemic's disruption of everyday life and in looking forward to the new normal. Totally, this figure shows the current generic emergency wireless communications framework for natural disasters and hot events. The LEO satellite network continuously maintains communication with the terrestrial cells based on the satellite group due to the rapid movement of LEO satellite. UAVs usually used as relays or area base stations communicate via terrestrial or satellite backhauling and achieve full coverage for emergency areas. The location of on-site command center is reasonably selected to facilitate communications for trapped users, which are irregularly distributed in emergency areas. Some trapped users are on the ground and connected to the satellites, UAVs, terrestrial base stations. The other trapped users are located in covered zones where they are masked or buried underground. The pandemic areas, multiple services such as remote education, telemedical medicine, video meeting, and mobile cabin hospital applications rely on infrastructure base stations. The information of emergency is sent back to the command center via the Earth gateway. Having reviewed the natural disaster and the hot events related emergencies, let's see the main challenges caused by emergencies. For quick and efficient recovery after disaster and hot events, emergency wireless communication, which provides a specified but agile communication mechanism for specified coverage, high capacity, and low latency in emergency situations, is very important in accident area and persistently requires novel wireless communications technologies for rescue capability enhancement. Actually, there are some typical characteristics of emergency communications. First, the emergencies are unforeseen. They often randomly occurred and thus cannot be very clearly estimated. Second, natural disasters are often with infrastructure destroyed and people covered or trapped underground, maybe underwater, also along with secondary disasters. For rescuing, a number of rescue institutions converge to the disaster area. On the other hand, hot events are with quicker response required, explosive data traffic, as well as chaotic scenes. Next, we propose the main challenges for emergency wireless communications. First, cascaded channel model for cross-medium communications. For complex emergency scenes, the channels are often cascaded. For example, two UAVs which work as temporary base stations to serve the trapped people. The signal which comes from the trapped people and goes to the command site undergoes 3 to 4 kinds of channels, such as the north channel from the command site to UAVs, among UAVs, feeding channels from UAVs to the trapped people. Cascaded channel makes the emergency communications very difficult. Second, temporary performance is required by emergencies. However, how to provide flexible and ubiquitous connectivity for trapped people is very challenging. Third, in disaster area, some people are trapped underground or even underwater. For efficient rescuing, how to achieve high rate for communications to soil or water under a covered space is very challenging. Last but not the least, for different types of traffic, such as command, data, as well as video, the quality of service requirements are different. How to guarantee diverse quality of service requirements for emergency cases is very challenging. Corresponding to aforementioned 4 main challenges, that is the cascaded channel model for cross-medium communications, flexible deployment for ubiquitous connectivity, deep propagation for more spectrum exploitation, distributed data service for quality of service. These 4 types of new or enhanced technology can be reformed or developed to meet the critical requirements of emergency wireless communications. In this tutorial, we mainly focus on the following 5 technologies. They are emergency wireless communications based complex channel modeling, UAVs enhanced communications, reconfigurable intelligent surface empowered communications, through the earth, or often says underground, underwater communications, diverse quality of service guarantees for emergency wireless communications networks. Next, in view of the aforementioned challenges, in part 2, I got to discuss several novel emergency wireless communications technologies. Some of them are based on recent developed or developing 5G and or 6G technologies. First of all, different from existing emergency wireless communications related works, we rethink and start with the channel of emergency wireless communications. This is a typical post-earthquake or any other related natural disaster resulted emergency scenario. The ground building somehow destroyed, along with the collapse of part of underground buildings. The traditional severe wireless communications is not designed according to emergency cases. For communications channel between the ground user and the underground user, it is not applicable to directly use the traditional relay or Nakagami channel model. And a series of communication schemes which are actually specified designed for severe wireless communications are also not applicable for such emergency cases. For the case shown in this picture, since the trapped users are underground, actually this is an usual case for covered user in post-disaster area. That means the disjointed or collapsed building covered the trapped users. The shadowing factor should be paid much more attention than before. Then let's come back and see the effects of wireless communications channel. Fundamental wireless propagation effects include the microscopic feeding, that is large scale or slow feeding, and microscope, that is the small scale or fast feeding. Microscope feeding results from the shadowing effect that by buildings, foliage, and other objects. Microscope feeding results from multipulse, which occurs in indoor environments and also both microcellular and microcellular outdoor environments. As I mentioned in the last slide, shadowing is a dominating factor for emergency wireless communications channel. Actually, there exists some works thinking the shadowing dominated channel, which follows the composite shadowing feeding distributions. Both microscopic and microscopic feeding together are modeled by composite shadowing distributions, of which really log normal and Nakagami log normal are the two most common models. However, the probability density function of these two composite models are not closed form, making performance analysis of some applications difficult. Hence, several other composite models have been developed, including the Suzuki distribution, the kappa and the key and general key distributions, the G distribution, and the gamma distribution. Note that these models are approximations of the really log normal and Nakagami log normal models. Also, the emergency wireless communications-based complexity model, channel model needs to take disaster factors into consideration. When dealing with disaster scenarios such as landslides, volcanic eruptions, and earthquakes, it is highly demanded to take the terrain into account. The refraction and the penetration of electromagnetic waves at this moment. There will be a certain impact on electromagnetic waves of different frequencies, depending on the properties of the medium and the size of obstacles in the propagation process. Another example is the recent COVID-19, how to temporarily but quickly build reliable communicator links. In crowded medical scenarios, such as mobile cabin hospitals, is also an issue that emergency wireless communications need to pay attention to. In view of the above factors, we can know that the difficulties for emergency wireless communications channel is the integration of disaster factors into channel model. Actually, since there exist diverse channel models we can follow, the difficulty of the emergency wireless communications channel model mainly focuses on the complexity of mathematical derivation and the applicability of the channel model. The mathematical closed form of the emergency wireless communications channel model, like the power density function of singular envelope, usually requires advanced mathematical functions, such as the Meyer-G function and modified Bessel function. Also, the channel model expression needs to be adaptive to the actual disaster scenarios. Commonly used composite channel models are shown here, as well as the probability distribution functions of the received singular SNR corresponding to these models. We can see from these models that the probability distribution function form of the received single SNR is extremely complex. So a general channel model, which can reflect the inherent of emergency wireless channels, is highly demanded. Researchers have spent a lot of time in optimizing the complexity of these models, and the main purpose is to build a simple channel model that can be used for a serious emergency scenarios. As shown in this figure, we show the emergency wireless communication system that includes the on-site command center, key 5G UAVs integrated with RIS, that is reconfigurable intelligent surfaces, each consisting of passive reflector elements, and the irregularly distributed trapped users in the post-disaster area. Under such an emergency wireless communication scenarios, there is only one on-site command center for sending, receiving, rescuing instructions within one local post-disaster area to serve nearby trapped users. Consequently, the location of on-site command center, which plays an important role in the rescue process, is reasonably selected to facilitate communications with the trapped users in the post-disaster areas. For example, in the figure, area C is selected for the on-site command center in this figure. This is because as this area, there is a relatively good channel, that is a lost channel from the on-site command to the 5G UAV. Then the on-site commander can communicate well to the trapped users for more efficient receiving operations. The channel from the UAV to the trapped person on the ground follows the Fisher-Snyder curve, that is the F distribution. The Fisher-Snyder curve F distribution is proposed as an accurate and tractable composite model to capture the multipath feeding and shattering conditions in practical wireless propagation scenarios in the previous literature. We recall that the derivation of F distribution channel. Traditionally, composite feeding models have considered a mixture of log-normal shattering and the classical multipath feeding models, such as the Rayleigh Rice, Nakagami M, or Hoyt. However, the main drawbacks is that it renders most of the corresponding statistics of interest analytically intractable. To overcome this issue, the gamma distribution has been proposed as an approximation to log normal distribution to describe shadowing. Based on this, the square root of a gamma random variable follows a Nakagami M distribution. Exploring this property, a new composite feeding channel is considered, in which the scattered multipath contribution follows a Nakagami M distribution, while a root mean square signal is shifted by an inverse Nakagami M distribution. It is demonstrated that this composite probability density function is functionally equivalent to the Fisher-Snyder F distribution. Furthermore, we consider the UAVs-based emergency wireless communications channel model, which is based on the novel heterogeneous F composite feeding and can accurately model as well as characterize the composite feeding channel with reflectors, path loss exponent, feeding, and sharing parameters. It shows here are the figures, some figures shows here. First, it shows the power density function of heterogeneous F composite feeding channel versus the channel characteristics of power gain, that is H, and the number of 5G UAVs. Here the number is key. When the number of 5G UAVs increases, the power density function of heterogeneous F composite feeding channel shifts to the right, which tend towards a large power gain. Therefore, we find that the average power gain H increases as the number of 5G UAVs increases. The power density function of heterogeneous F composite feeding channel versus the power gain H with different number of reflectors, that is N, is shown in the figure on the right hand. It is clear that the curve shifts to the right corresponding to large power gains as N, that is the number of reflectors, increases. It shows the power density function of heterogeneous F composite feeding channel versus the channel characteristics of power gain H and the number of reflectors N. Actually, the MS is a specific parameter which can reflect the shadowing degree corresponding to the emergency wireless communications channel. These two figures show that the minor changes, that the power gain very likely increases as the parameter MS increases and alpha decreases. The alpha is related to the path loss exponent. In detail, figure on the left hand shows the power density function of heterogeneous F composite feeding channel versus the channel characteristics of power gain and the shadowing parameter NS. It can be seen from this figure that the range of achievable power gain is gradually concentrated as the shadowing parameter increases. This is because that the links on the go more slightly shadowing as MS increases. Then figure on the right hand shows the power density probability density function of heterogeneous F composite feeding channel versus the channel characteristics of power gain H and the power loss exponent alpha. We observe that the average power gain also increases as the path loss exponent alpha decreases. In summary, there is a better average power gain as the number of reflectors increases. The power loss exponent decreases and the shadowing parameter increases, which are consistent with the practical emergency communication scenario. Furthermore, we have improved this channel model with removing the assumptions that the reflected signals of each reconfigurable intelligent surface are independent with each other, and turning the sum of the scores of multiple received signals into the score of the sum of multiple received signals. The details can be found in the paper. That is our paper, performance analysis of risk-equipped UAV-based emergency wireless communications, that will be presented in IEEE ICC this year. Having considered the specific characteristics of channels models for emergency wireless communications, we discussed the UAV's enhanced emergency wireless communications, which can provide temporary but convenient communication links for disaster scenarios, as well as hot events scenarios. Recent advances in manufacturing communications sensors, electronics, and control technology have witnessed an unprecedented application increase of UAVs in the emergency, civil, and public affairs. For example, emergency rescue and communications, border patrol, navigation and positioning, monitoring, and detection. Based on the applications, UAVs can be used for delivery, sensing, and attack. They can differ in networking, varying degree, routing skill, and control method. Like delivery, there are many applications in which UAV-assisted wireless infrastructure needs to be established for providing area-wide coverage. Disaster-struck areas, remote villages, or deep-sea oil rigs would all require quick deployment of UAV-based network that can provide voice, video, and data service. In these applications, the UAVs hover over the area and are often relatively stationary. These can be considered to be cellular towers or wireless access points in the sky. In contrast, sensing applications like detection of forest fires or survey of a corpse would require mobile UAVs. Early uses of UAV were characterized by use of a single large UAV for a task. In these systems, the UAV-based communication network, therefore, consists of just one area load and one or more ground loads. Today, most public and civil applications can be carried out more efficiently with multiple UAV systems. In a multiple UAV system, the UAVs are smaller and less expensive and work in a coordinated manner. In most multiple UAV systems, the communication network supporting communication among UAVs and between the UAVs and the ground nodes becomes more and more important. As these UAVs can be configured to provide service cooperatively and extend the network coverage by acting as a relays. The degree of mobility of UAVs depends on the application. For instance, in providing communication over an earthquake-struck area, the UAVs would hover over the area of operation and the links would be slow dynamic. As opposed to these applications like agriculture or forest surveillance require the UAVs to move across a large area and links frequently, break and re-establish. The dynamic nature of the network configuration and links is apparently different from the fact that the UAVs may go out of service periodically due to malfunction or battery drainage. To exploit the functions of different UAVs, the rise of UAV fleet technologies for emergency wireless communications in harsh environments should be considered. For example, the multi-tier heterogeneous UAV network, here that's often called the Wuhan, the multiple heterogeneous UAV network, which includes the heterogeneous UAV fleets in different altitudes in the flexible network architecture to cope with various emergencies. Wuhan inherently has the advantage to energize emergency wireless communication network that provides expanded coverage and effective communications for comprehensive services. Here, the emergency wireless communication network is called the ECOLAT. As a large-scale heterogeneous network with a complex structure, high flexibility, and dynamic topology, the Wuhan faces a variety of special challenges for emergency communications, like a complex channel model, limited energy supply, competitive heatness, resource management, and the jittering effect. Driven by the requirements of coverage, spectrum efficiency, energy efficiency, and heterogeneous network integration, Wuhan-based EcoLabs lead refined designs to overcome these challenges. To extend the wireless coverage and increase the cooperative spectrum efficiency, and as well as energy efficiency, some problems are required to be resolved. For emergencies, it is highly expected for Wuhan-based EcoLabs to serve the dead zones where existing communications infrastructures are destroyed or overloaded. However, this kind of full coverage requirement imposes new challenges for Wuhan-based EcoLabs. First, how to provide continuous communication services for multiple trapped users irregularly distributed at emergency areas. Second, in some disasters such as earthquake, hurricane, and mudslides, the trapped users are very likely to be masked by the obstacles, shadows, or buried under the ground, and very hard to obtain timely and stable connections. Therefore, it is necessary to exploit advanced techniques for achieving full coverage on the Wuhan-based satellites. The promising solutions about deployment plan, power optimization, hybrid beamforming, and above-based joint design will be discussed. For UAV deployment, two optimizations, that is, the placement and the trajectory, plays important roles. First, placement optimization. In terrestrial communication networks without fixed infrastructure, UAV stations provide an efficient solution to achieve wireless connectivities. It aims to minimize the number of UAVs needed to provide wireless coverage, to extend wireless coverage for a group of distributed ground terminals, or maybe some users are buried under the ground. Ensure that each ground terminal is within the communication range of at least one UAV. Then, the joint trajectory and power optimization is also common. We investigate the minimization of the movement distance of UAV under two constraints. The first constraint, the ground user is only served by one UAV in one communication parallel time. And constraint 2, the user should select the UAV which is closest to himself to communicate for communication to increase the transmission power gain and reduce the co-channel interference. Here is the numeric results. The numeric results show that the average rate per unit area increases as the number of UAVs increases. So this is consistent with the common sense that for the disaster area, more UAVs can work, or more UAVs can cooperatively work for rescuing people or for efficient saving. With the joint optimization of the trajectory and power, the system can achieve larger weight. So this is the clear results. By considering UAV heterogeneity to cover the whole target area, other research studies studies two fast UAV deployment problems. One is to minimize the maximum deployment delay among all UAVs. That is the typical min-max problem for fairness consideration. And the other one is to minimize the total deployment delay. That is for the efficiency consideration. Furthermore, the 2D extension deployment algorithm was also investigated. Besides, hybrid beamforming shows the higher performance gain in UAV enhanced emergency wireless communication. This figure shows the considered multiple UAV-aided downlink mmWave communication network, where hybrid beamforming and analog beamforming structures are employed at a UAV to the base stations and the ground users respectively. To maximize the ASI of the ground users, the problem for joint optimization of the UAV positioning is formulated. We are constraint one. This is constraint one ensures that the number of users collected to each UAV base station does not exceed the number of the off-chain. The second constraint indicates that all the users should be served by the UAV base stations. The third constraint guarantees that each user is served by one UAV base station at most. The fourth constraint is the modulus constraint on the analog beamforming matrices of the UAV base stations. The fifth constraint ensures that the transmit power of each UAV base station cannot exceed a maximum value, that is P. The sixth constraint is the constant modulus constraint on the analog beamforming vectors of the users. The seventh constraint guarantees that the achievable rate of each user is no less than the required rate, that is the minimum rate. Here, the simulation is regarding the achievable sum rate of the proposed solution versus the AOD errors caused by the UAV jittering, with a array size that is 16 by 16, 8 by 8, or 4 by 4 at the UAV base stations. The proposed hybrid beamforming solution closely approaches the performance bound given by fully digital beamforming. Furthermore, a full duplex UAV relay is exploited to increase the communication capacity of millimeter wave networks by jointly optimizing position, beamforming, and power control. Here, simulation results demonstrate that the proposed positioning, beamforming, and power control method for the millimeter wave full duplex UAV relay system can closely approach a performance upper bound in terms of the achievable rate and significantly outperforms the other three benchmark schemes. In disaster or hot events impacted areas, the instantaneous high volume traffic such as the dispatch instructions from the command center and the feedback information from trapped users and the frontline rescuers results in overloaded communication infrastructure and network congestion. Also, the path loss, fading, ring attenuation, and shadowing parameters seriously decrease the long-distance transmission rate due to the harsh environment in the accident area. Therefore, the network capacity is a key indicator for the explosive growth of traffic transmission. How to increase the network capacity with the limited emergency communication resources is the second bottleneck. Most of the solutions are presented in the previous reports, such as deployment plan, trajectory optimization, as well as the hybrid beamforming. Next, we focus on the resource allocation based on the complex channel model. In view of such complex channel conditions, it is very critical to characterize the shadowing parameters, that is the MS, and derive the new hybrid channel model. The shadowing parameter MS, which follows the inverse Nakagami M distribution in F composite feeding channel, represents severe shadowing as MS goes to 0 and weak shadowing as MS goes to infinite. Based on the complex channel model, the adaptive resource allocation schemes are proposed. We compare the capacities of equivalent channel adopted resource allocation schemes and the capacities of traditional channel adapted resource allocation schemes. It shows that the application scenario of RIS UAV communications over Mohan-based equivalents. The link between on-site command center and the trapped users is partly interrupted since the collapsed buildings caused a blind spot for communication, shown as that is the dead zone. RIS UAV facilitates communications of trapped users. In this application scenario, the limited power and bandwidth are allocated corresponding to the variation of shadowing. It is illustrated that the equivalent channel adopted a joint power and bandwidth optimization scheme can achieve higher capacity than the other traditional schemes. For emergency wireless communications, UAVs are commonly used for supplementary coverage to resist harsh environments, which challenges the induration of UAVs. During hovering, UAVs consume much energy to fight against self-gravity and provide momentum to move forward. Since it is impossible for UAVs to always fly at a constant speed, the higher current discharge is required when encountering strong winds or higher speed requirements. Moreover, UAV communication performance guarantee must be taken into consideration, thus causing indispensable energy consumption. Therefore, the battery life of UAVs is very related to the stability of equivalents. Nowadays, MIMO-assisted UAVs are usually considered to increase the network capacity of emergency wireless communications. However, it cannot maintain long hours of work due to the limited energy supply resulted by the physical structure probability of UAVs. Under extremely harsh weather, UAVs are usually equipped with blade protection covers that are suitable for strong wind and rain. The blade protection cover increases the weight and power consumption of UAVs. For exploiting the flexibility and the long endurance of UAVs, it is not recommendable to carry out overweight and power consumed devices such as spare batteries and multiple antennas with large size. Clearly, energy efficiency is very important for UAV networks, as most of the energy has to be used for flying for a long time running. Thus, transmit power consumed in wireless transmission and signal processing should be as low as possible. In this sense, technologies with complicated signal processing are not suitable for UAV communications, like something like that used in the traditional MIMO. Also, it can increase the rate or the spectrum efficiency for the UAV-based communications. Apparently, this is not suitable for the emergency wireless communications. Therefore, a major concern that has always restricted the UAVs is how to achieve reliable communications with low transmit power. Here, we propose to exploit the advanced technology to increase the energy efficiency. Nowadays, reconfigurable intelligent surface-based wireless communications received much attention. Without expensive and complex IF chains, reconfigurable intelligent surface is treated as energy efficient and cost efficient, and can be expected to solve the energy efficiency related problems in emergency wireless communications. So next, we focus on reconfigurable intelligent surface empowered emergency wireless communications. To overcome some typical shortcomings of the UAVs on the many specific communication scenarios, such as the emergency wireless communication scenario, and further increase the channel capacity as well as the energy efficiency of emergency wireless communication systems. Reconfigurable intelligent surface as an emerging physical near technology attracted much attention. Reconfigurable intelligent surfaces have important advantages for practical implementations. As shown in this figure, a typical reconfigurable intelligent surface architecture mainly consists of the low-cost metal surface that possesses the ability to manipulate the propagation of an electromagnetic signal by either reflecting or refracting the signal to be adaptive to the dynamic fluctuation wireless propagation environment. First, reconfigurable intelligent surfaces can be deployed on several structures, including the building facades, indoor walls, aerial platforms, as well as the vehicle windows due to their low cost and easy employment, something like the properties. And the reflecting elements only passively reflect the incoming signals without any sophisticated signal processing operations that require the RF transceiver hardware. Hence, compared to conventional active transmitters, reconfigurable intelligent surfaces can operate at a much lower cost in terms of hardware and power consumption, which very fits the demand of emergency wireless communication scenario. Then, reconfigurable intelligent surfaces are capable of configuring the wireless propagation environment by compensating for the power loss over long distance. A virtual line of sight links between base stations and mobile users can be formed while passively reflecting the impinging radio signals. The throughput enhancement becomes significant when the lost link between the base stations and users is blocked by obstacles. For example, the high-rise buildings. Due to the intelligent deployment and design of reconfigurable intelligent surfaces, a software-defined wireless environment may be constructed, which in turn provides potential enhancements of the received SNR. Furthermore, in contrast to conventional relaying systems such as the amplifier and forwarder, or the decoder and forwarder, or the duplex relays, reconfigurable intelligent surfaces are capable of shipping the incoming signal by controlling the phase shift of each reflecting element instead of employing a power amplifier. Thus, deploying REIS is more energy efficient and environment friendly than conventional relaying systems. Additionally, RIS is of great compatibility because it supports full duplex and full band transmission due to the fact that it only reflects the electromagnetic waves. And the RIS enhanced voice levels are compatible with the standards and hardware of existing voice levels. In conclusion, RIS can be leveraged for enhancing the performance of emergency wireless communications by fully reaping the aforementioned benefits. Simultaneous wireless information and power transfer, that is SWIFT, is a promising technology for providing cost-effective power delivery to limited Internet of Things levels. Cheng and Zhang are considered and RIS being deployed to assist multi-antenna access points to serve multiple information decoding receivers and energy harvesting receivers. The problem is maximizing the weighted sum power received by the energy harvesting receivers, subject to the individual similar to interference plus noise ratio constraints for the information decoding receivers. Then jointly optimizing the transmitter precoders at the access point and reflecting phase shifts at the RIS, the higher RIS can be achieved. Simulation results show significant performance gain achieved by their proposed designs. Since RIS can easily be deployed and smartly reconfigures the wireless propagation environments with very low energy consumption, aerial RIS was proposed to extend coverage with panoramic or full-angle reflection, in which RIS is integrated with UAVs or balloons. It is worth mentioning that each small scatter can be programmed by digital sequence to achieve real-time control of electromagnetic parameters without extra power consumption. Following that, the lightweight integration and passive beamforming of RIS are helpful for UAV communications. Moreover, RIS-assisted communications services and applications have been investigated on different communication systems, which verify the potential of capacity and energy efficiency enhancements. Therefore, the RIS UAV communication is suitable to refine the performance of Wuhan-based acrolets. The performances of energy efficiency with the minor UAVs and the RIS UAVs are evaluated in this figure. That is on the right hand. Where K denotes the antenna number of minor UAVs and denotes the reflective elements number of the RIS UAVs. As shown in this figure, it is clear that the RIS UAVs can achieve higher energy efficiency than traditional UAVs. Furthermore, under the hot events, where massive sensors and large things together, simultaneous wireless information and power transfer and SWIFT system can be effective. This paper investigates reconfigurable intelligent service-assisted simultaneous wireless information and power transfer system. Multiple RIS deployed on UAVs and ground buildings are considered in the proposed system for enhancing transmission of information and energy simultaneously. The optimization problem is formulated to maximize the average achievable rate over n times slots by jointly optimizing power splitting ratio, transmit beamforming, phase shifts, and the trajectories of UAVs. We can observe that achievable rate increases with the number of reflecting elements going into larger. That we can see from the figure A on the right, on the left hand. Furthermore, UAV's trajectories can be seen from the figure B on the right hand. The deployments of multiple devices have an influence on trajectories of UAVs. A base station with more than one antenna can impact the will impact the trajectories heavily impact. Therefore, UAVs have spent more time hovering on the above base station. Here this is in figure B. As discussed aforementioned, UAVs provide immense advantages because of coverage, the coverage, data collection, connectivity among devices, easy deployment, and precision monitoring. So the integration between the integration of RIS and UAV creates an innovative space to provide enormous service to the users. Therefore, the following focuses on the UAV assisted RIS system. Lu and Zhang, as well as Cheng and Zhang, proposed a new three-dimensional networking architecture enabled by area intelligent reflecting surfaces to achieve panoramic signal reflection from the sky. The problem is maximizing the worst case signal to noise ratio in a given area, a given coverage area, and with jointly optimizing the transmitter beamforming of the resource node, the placement and phase shifts of the area RIS can be optimized. To achieve the high SNR. Then, numeric results show that the received SNR increases, significantly increases with the aid of RIS, which means that the proposed design can achieve significant performance gains with the aid of RIS. Next, an integrated UAV RIS system that can operate in three different models, such as UAV RIS and UAV plus RIS, is considered. UAV only mode means that UAV performs relaying in full duplex mode. A RIS only mode means a RIS only performs reflective relaying without self-interference consideration. And integrated UAV RIS model means that both UAV and RIS perform reading, and the receiver uses selection combining to choose the mode. For the proposed modes, exact and approximate expressions for the end-to-end outage probability and energy efficiency in closed form are given. The simulation results show that as the number of reflecting elements n increases, the RIS-only mode and the integrated UAV plus RIS mode minimize the outage probability and maximize the capacity. It's because the RIS enhanced the transmission link. Then, the authors optimize key system parameters such as the UAV altitude and the number of elements on the RIS considering different modes, and consider the two optimization problems for maximize the network energy efficiency and minimize the network power consumption subject to system parameters and read constraints. The simulation results reveal that optimal mode selection is important for energy efficiency on the different parameter settings, such as the distance between source to UAV and the number of reflecting elements. That is a typical parameter for the RIS for the reconfigurable intelligent surfaces. Under some circumstances, the performance of RIS-only mode is much better than that of UAV-only mode. Therefore, the receiver should choose the optimal mode to achieve the best performance. For the performance analysis of equipped system, we consider RIS-equipped UAV-based emergency wireless communication systems and the channel experience official cylindrical F feeding, which fits the emergency wireless communications scenario. And in the paper that is to be presented in ICC this year, fixed wing UAV hovers over the post-disaster area as a temporary base station, carrying a large RIS to assist the communication with distributed trapped users. Here, RIS works as a multiple channel transmitter to accomplish the direct modulation and transmission of wireless signals. Then we use central limited theory based and gamma-based approximation to present closed form expression of the new channel statistics for power density function and the cumulative density function, tube reach, bit error reach, and outage probability. The numerical results validate the analysis in the previous sections. The figures show that the system can achieve improvement by ending the number of n, which means the remarkable benefits of employing RIS with the channel experiencing severe feeding and shadowing on the emergency wireless communications scenario. However, there are two problems. One is the CRT-based and gamma-based distributions are not completely exact. Second, the assumption of perfectly instantaneous CSI is unrealistic in practical, which makes the performance analysis of RIS-assisted systems an interesting problem for future research. Although RIS can indeed appealing for the above applications, their implementation possesses several challenges as well. In the following, we list some promising future research directions. In real-world scenarios, especially in emergency wireless communication scenarios, UAV-assisted RIS system makes channel modeling sophisticated and challenging due to the terrain changes caused by secondary disasters and high mobility of UAVs. Additionally, when the number of reflecting elements is very large, the cascaded channel contains a large number of channel coefficients. Hence, their establishing requires a large number of pilots, which is a proportion to the number of reflecting elements. How to reduce the channel estimations overhead remains an open problem. To our observation from the studies, in most of the cases, most of the existing contributions are based on the assumption that the performance, the perfect instantaneous CSI can be gauged, which is unrealistic in practice. Acquiring the near instantaneous CSI may be very challenging for the following reasons. First, the training overhead is excessive when the number of reflecting elements is large. Second, the base station has to compute its beamforming reads, as well as phase shifts at the reads, which entails solving a large-scale optimization problem. Third, when the number of RIS elements is large and the channel is rapidly varying, the required capacity of the feedback link from the base station to the RIS also increases, which imposes the high overhead and high cost. To address these challenges, it is appealing to design the phase shift based on the long-term CSI, relying on both angular and location information. Most existing contributions related to RIS have considered channel estimation for time division duplex-based implementation due to the appealing feature of channel reciprocity. However, recent results reveal that the RIS phase shift model depends on the incident electromagnetic angles, which implies that the assumption of channel reciprocity in TDD systems may not hold in practice. Hence, it is imperative to study channel estimation and transmission design for frequency division duplex RIS systems. More than the air-based or terrestrial-based emergency wireless communications, one of the key problems for emergency rescuing is the through-the-earth communications ability. In the following, I discuss the through-the-earth communications with some recent developed low technologies. Our commonly used communication devices are generally based on electromagnetic waves. However, traditional communication techniques with electromagnetic waves do not work well in underground environments due to the very high material absorption loss. An alternative and efficient communication technique is designed to be used for through-the-earth transmission. Magnetic induction has been shown to be a good choice due to the advantages of high penetration efficiency, stable channel, and small antenna size. The system model and the equivalent circuit for MITTE, that is magnetic induction through the earth communications, are shown in this left-hand side. Magnetic induction through the earth communications are based on the Faraday's electromagnetic induction law and use the magnetic field generated by core antennas to exchange transmission in near field. There are three main challenges for MITTE communications. The first one is orientation problem. This is because the path loss of MITTE communications is sensitive to the core orientation. The second challenge is the transmission range extension. This is because the power of a magnetic field attenuates at the sixth power of the distance. Also, the eddy current loss in underground scenarios increases exponentially as the transmission range increases. The third challenge is capacity enhancement. This is because the path loss significantly increases as the operating frequency derivates from the resonant frequency, and this leads to a narrow bandwidth. The orientation problem of magnetic induction through the Earth communications can be solved from the perspective of coin antenna designs. Here are three pictures showing three different kinds of coins. The related works include the first picture, that is the triple directional coins, and the second is meta material enhanced MI coins, and the third one is spherical coin array closed loop coins. To extend the transmission range for MITTE communications, waveguide techniques can be used. In MITTE waveguide techniques, multiple passive relays without power source can be used between the transmitter and the receiver to induce time-varying currents one by one and convey the MI waves. Thus, the transmission distance is dramatically extended. To further extend the transmission distance, some active relays with the power source can be deployed to repeat and retransmit the received signals. This kind of waveguide techniques are called hybrid MITTE waveguide techniques. The longer transmission ranges can be achieved if more active relays are deployed, while less energy is consumed if more passive relays are deployed. It should be noticed that the coin antenna design scheme such as triple directional coins, metamaterial enhanced MI coins, and spherical coin array enclosed loop coins can be also used in waveguide techniques to solve the orientation problem or enhance the magnetic field. The relationships between path loss and operating frequency are shown in the left-hand slide. We can see that the path loss significantly increases as the operation frequency derives from the resultant frequency. Thus, the bandwidth of magnetic induction through the Earth's communications is narrow. It can be observed that the 3 dB bandwidth of MITT communication is in the order of kHz. Thus, the capacity of MITT communications can be enhanced from two aspects. First one is the bandwidth extension, that is, generate more resultant frequencies. The second one is spectrum efficiency enhancement, that is, increase the tube rate corresponding to each frequency band around the resonant frequency. The capacity enhancement for MITT communications is our focus. To generate more resonant frequencies for MITT communications, multiple frequency resonating composition coins, we call that the MURAC, that is, can be used. The equivalent circuit for MURAC coins are shown in the left-hand side. As compared with traditional coins, MURAC coins are equipped with MURAC circuit to generate multiple resonant frequencies. The impedance characteristic of MURAC coins is shown in the right-hand side. We can see that the MURAC coins have multiple resonant frequencies. With multiple resonant frequencies generated by MURAC coins, we can realize multiple user transmission based on multiple frequency access. An MI-based slipped network with multiple frequency access can be formulated as shown in the left-hand side. Multiple MURAC coins are equipped for access point to access multiple receivers with frequency domain resources. The AP simultaneously delivers the information and wisely charges the receivers. Each receiver has one resonant frequency and access one frequency domain channel provided by the access point. Then, to enhance the spectrum efficiency for the slipped network, we use magnetic beamforming technique. The magnetic beamforming scheme can be obtained by solving the problem, this is problem 1, the P1. It aims to minimize the transmitted power under the constraints of total throughput, delivered power, and individual requirement of each channel. P1 is actually non-convex and difficult to be directly solved. After semi-definite relaxation, and we can obtain the convex problem P1 SDR here on the right hand. By solving P1 SDR problem and adding the pseudoloids, we can obtain the beamforming vector. In the paper that is to be seen in 2022, we have proven that the obtained beamforming vector is approximately optimal. Next, we discuss a special case for MITT slipped, where access point only delivers information and does not charge receivers. The corresponding magnetic beamforming schemes can be obtained by solving the problem P2. It aims to minimize the transmitted power under the constraints of total throughput and the individual reach of each channel. P2 is actually also non-convex and difficult to be directly solved. In the paper shown as a list, we find an optimality condition for P2. Based on the optimality condition, problem P2 can be converted to the third problem, that is P3. P3 is convex. Solving P3, we can obtain the globally optimal beamforming vector in closed form. Another special case for MITT Swift is MITT wireless power transfer, where the access point only charges the receiver and does not deliver information. The corresponding magnetic beamforming scheme can be obtained by solving the problem P4 for the first problem. It aims to minimize the transmitted power under the constraints of total delivered power and the individual delivered power of each channel. After semi-definite relaxation, we can obtain a convex problem P4 SDR. In our paper, we have proven that the rank of the optimal solution to problem P4 SDR can always be reduced to 1 using rank reduction procedures while guaranteeing the strong duality. Thus, the global optimal beamforming vector can be obtained by solving P4 SDR and making the corresponding eigenvalue decomposition. As compared with MITT Swift, the beamforming scheme corresponding to MITT wireless power transfer can achieve the globally optimal value without assistance of residual losses. These are some numerical results for MITT transmission with multiple frequency access. We can obtain the 3 conclusions from the results. First, the Murat points combined with the proposed beamforming schemes can always achieve better performance than traditional schemes. The second, the performance gain increases as the transmission distance increases. This is an interesting result. The third one, if the coins are weakly coupled, the proposed beamforming schemes are close to the traditional beamforming schemes. Another solution for capacity enhancement is the MISO OFDM-based MITT communications. The spectrum efficiency is enhanced from 2 aspects. First, the power gain provided by antenna resources are used to enhance the spectrum efficiency. Second, to cope with frequency selective feeding caused by coins, resident frequencies and non-resident frequencies are comprehensively utilized, which is based on the OFDM modulation. Next, to enhance the spectrum efficiency for MISO OFDM-based MITT communications, we find the optimal current control scheme. The optimal current control scheme can be obtained by solving problem P1. It aims to maximize the sum rate under the constraint of power consumption. Problem P1 is also actually non-convex and difficult to be directly solved. In this paper, we found an optimality condition for problem P1. And also based on the optimality condition, problem P1 can be converted to another problem P2. And P2 is also convex. Solving P2, we can obtain the globally optimal beamforming vector in closed form. If the number of subcarriers is set large, the approximate expression for MISO magnetic induction channel can be obtained. These are some numerical results for MIMO OFDM-based MITT communications. We can obtain the 2 conclusions from the results. First, OFDM modulation can increase the capacity of MITT communications. It enhances the rates corresponding to long resonant frequencies at the cost of rates corresponding to resonant frequencies. Second, with given bandwidth and power constraints, the capacity increases as the number of subcarrier and antennas increase. Last but not the least, quality of service guarantee is always the important and key problem for wireless communications. For emergency wireless communications, the low latency, as well as diverse quality of service guarantees, become even more important due to the urgency of emergencies. However, the quality, diversity, as well as the dynamic range of emergency wireless communications are relatively large, which make the quality of service which make the quality of service guarantees of emergency wireless communications very challenging. In disaster environment, next generation emergency services are expected to utilize all the emergency technical innovations to enhance both the user's experience when calling an emergency and the first responders' situation awareness while in the area of event. One of the potential enablers for this advantage is the deployment of a massive number of sensors and haptic devices, and thus forming a global Internet of Things. Evidently, future emergency wireless communications will be heavily relying on sensors either dispersed in buildings, road lines, or vehicles, or carried as wearables by first responders, persons of interest, or people in need of remote health monitoring. Hence, creating a massive Internet of Things connected to the network on a massive scale. In order to satisfy the strict requirements imposed by emergency communications and public protections and disaster relief service in general, the network operators are expected to ensure ultra-low latency, ultra-high availability, and reliability for these services. New architecture and framework of emergency communications are expected to support real-time, high-priority total conversation service, that is the voice, video, real-time, as well as text. Thus, create an always connected experience for the emergency workers and rendering them capable of utilizing high-quality multimedia content for improved awareness. It is clear that various sorts of enhancements are required in order to fulfill the requirements of ultra-low latency applications. Here are some potential solutions summarized as a table to address the mentioned challenges. The research on delay reduction mainly includes the following aspects. First, multiple access protocol. Second, scheduling strategy. Third, channel coding scheme. Fourth, resource management. Fifth, queuing behavior modeling. The last one, frame structure design. For the uplink, a significant part of delay comes from the exchange of a scheduling request and uplink transmission granted between the user and the base station. To meet stringent delay requirements in emergency wireless communications, the novel grant-free random access protocol was proposed in NR to accommodate a massive access within the delay limit. Different from the traditional grant-based access procedure with four-way handshaking in LTE, the grant request step has been removed in two-step grant-free access, where additional delay and overhead can be avoided. However, grant-free access incurs potential collisions because the channels are no longer reserved for specific packets. To solve this problem, three improved grant-free transmission schemes, that is, reactive grant-free transmission, a key repetition grant-free transmission, proactive grant-free transmission were proposed. Studies have shown that first, the either key repetition scheme or proactive scheme provides lower access failure probability than the reactive scheme, except higher density and lower SNR threshold scenarios. Second, Under shorter low latency constraints, the proactive scheme provides the lowest access failure probabilities. Third, under longer latency constraints, the key repetition scheme provides the lowest access failure probability, which depends on key, the key needs to be optimized. As for channel coding scheme, several candidate channel codes, including power codes, turbo codes, LDTC codes, convolutional codes, and BCH codes, were considered and compared in terms of block error rate on the optimal decoder, rate performance on the practical decoders, and the algorithmic complexity of decoding algorithms. BCH codes provide the highest reliability on the optimal decoding, since they have the highest minimum Hamming distance. Power codes with successive cancellation list decoding provide high reliability with only 0.5 dB gap to the normal approximation with reasonable complexity. Besides, resource management is a major issue and open problems still remain to be resolved in resource optimization for delay reduction for emergency wireless communications. For low latency service with small packet size, resources allocated to control signaling should be carefully designed. Simulation shows that reliability of control signaling can be improved by proper selection of time-frequency resources, transmit power, number of antennas, modulation schemes, and channel codes. However, how to optimize resource allocation for uplink, downlink control signaling and data transmission has not been considered in the existing literature. A large part of control overhead comes from channel estimation in a closed-loop transmission strategy. If more training resources are used to estimate channel state information, more accurate CSI can be obtained, but less resources remain for data transmission. Alternatively, we can consider an open-loop downlink transmission strategy. For example, the base station simply broadcasts the received packets to all mobile users without the need to estimate CSI. It is unclear the open loop or the closed loop strategy requires less resources. Among candidate labels for solving this complex, dynamic, and time-limited resource management problem, artificial intelligence is promising. In light of recent advances in computing and storage technologies, AI is making the leap from traditional pattern recognition use cases to governing complex systems through advanced machine learning approaches. The machine learning powered intelligent resource management problem was divided into three sub-problems. First is the radio resource provisioning, that is RRP, and the radio resource scheduling, that is RRS, as well as the third one, the radio resource utilization, that is RRU. Proactive resource provisioning based on training and prediction is done at the RAN control center. The RRP at the RAN control center benefits from the following three parts. The first one is the inter-transfer learning. The second one is the federated learning of a mobility pattern. The third one is the risk-aware online learning for RRP updates. The RS at base stations benefits from the first one is the regression-based user radio map updates. The second one is the risk-aware online learning for RS updates. RRU at the end devices benefit from the risk-aware online learning for RRU updates. In current wireless communications, the over-the-air delay consists of transmission delay, queuing delay, processing delay, and propagation delay. Processing delay is highly dependent on the processing capability of the hardware and usually the order of microseconds or less. Propagation delay depends on the propagation distance and the propagation speed, where the propagation speed is determined by the physical medium of the link. Propagation delay is not a bottleneck in reducing the end-to-end delay currently because it is much smaller than other delays. Compared with other delays, queuing delay and transmission delay are very important parts of the over-the-air delay. For queuing delay, two key performance indicators have been fully researched in existing literatures. One is the average queuing delay, and the other is the upper bound of queuing delay. To minimize the average queuing delay, queuing theory has been widely applied in wireless communications. On the other hand, to minimize the upper bound of the queuing delay, the large deviation principle has been widely employed. Apart from the queuing delay, transmission delay is another main component of over-the-air delay. In LTE works, the minimum transmission time interval was set to 1 millisecond. Such a transmission delay limits the low bound of end-to-end delay. To break through the end-to-end delay limitation of minimum TTI constraints in LTE, a shorter TTI was proposed for the 5G NR. The shorter TTI of 5G NR was said to be less than 1 millisecond, that is 0.0625 milliseconds, 0.125 milliseconds, 0.25 milliseconds, 0.5 milliseconds. Such a TTI empowers the end-to-end delay of 5G to be millisecond level. The short TTR in new radio corresponds to shorter frame structure, that is finite block length transmission. However, existing studies aiming at reducing delay with a fixed transmission time interval. With the constant bandwidth policy, the fixed TTI corresponds to the fixed block length. Specifically, as shown in this figure, the achievable rate in the finite block length region implies that the achievable rate decreases as the block length decreases. As the achievable rate decreases, the queuing delay increases. Meanwhile, the transmission delay decreases as block length decreases. As a result, we can conclude that as the finite block length decreases, the transmission delay decreases while the queuing delay increases. Thus, there exists a trade-off between the queuing delay and the transmission delay. Such a phenomenon indicates that there exists an optimal adaptive block length scheme, which can balance the queuing delay and transmission delay, thus reducing the overall delay compared with that of the fixed block length. To fully consider the overall delay reduction problem, the flexible frame structure are highly demanded. Therefore, we propose an adaptive frame structure which can adaptively change the block length. First, we propose an adaptive frame structure for single use case. To achieve the optimal balance between queuing delay and transmission delay, we propose an adaptive block length transmission framework, which means the block length of each frame can be changed adaptively. A dynamic buffering model for variable transmission time interval is introduced for the time varying arrival of packets adaptation. To further reduce delay, we formulate the average end-to-end delay minimization problem. Then we propose the flexible proximal alternating direction method of multipliers scheme to minimize the important part of the end-to-end delay for the single user case. The picture on the left shows the block length of adaptive frame structure and the constant frame in LTE and new radio. It can be seen from the figure that the block length is constant for LTE and new radio. For our proposed adaptive frame structure, the frame length gradually decreases as the frame index increases. This is because long frame length with large service rate is used for early part of arrival packets to reduce the queuing delay, while short frame length is used for later arrival packets to reduce the transmission delay. The picture on the right shows the delay performance comparison of adaptive frame structure with standard frame length in LT and new video. On the same total consumption time, the adaptive frame structure can achieve lower average end-to-end delay. For multiple use cases, the time frequency resources are shared. Optimizing the block length for multiple use cases is to adaptively allocate time and available frequency for each other. The orthogonal bandwidth allocation scheme is employed here, which brings the discrete constraint to the non-convex problem. Deep reinforcement learning has been considered as a candidate to solve complex and non-convex problems. Thus, we use multiple DQing to solve the average end-to-end delay minimization problem in multiple use cases. The picture on the left shows the remote and convergence performance of different reinforcement learning strategies. It can be seen from the figure that the single DQ cannot converge to the optimal block length due to the large step size. The convergence speed of DDPG DQing is slow. The multiple DQing can converge to the optimal result at a fast speed. The picture on the right shows the delay performance comparison of adaptive frame structure with standard frame length in LT and new video in multiple use cases. Our proposed adaptive framework structure achieves the minimum average end-to-end delay, meanwhile consuming little time to transmit all of arrival packets. Next, we are going to the third part, future trends, intelligent emergency wireless communications. This is also the future goal of our regarding our emergency wireless communications design. Most of the researchers focus on communication system at the disaster area nowadays. In the previous discussion, we are aiming at the channel model on site, wireless coverage, spectrum efficiency, energy efficiency, and as well as the data rate. However, pre-disaster warning, risk assessment, and post-disaster construction are also very important. Therefore, intelligent emergency wireless communications, which means aggregating all the emergency resources to timely perception, processing, communication, and decision making is our ultimate goal. To achieve intelligent emergency wireless communications, the disaster prediction and the post-disaster reconstruction need to be considered to achieve circularly intelligent emergency wireless communications. From disaster prediction and risk assessment to post-disaster reconstruction, there are several tasks that we still have to do. As a critical link for signal propagation, the intelligence of channel modeling is an important part. Besides, there are a large number of sensors deployed in places where disaster frequently bursts, which collect terrain and weather information in a timely manner and perform data transmission and processing constantly. Furthermore, due to the participation of different communication mechanisms, heterogeneous networks integration impacts the quality of service. Therefore, the diverse services, including underground service, high priority service, and so on, are required to be covered. Next, in response to the above issues, we list some future research directions, including but not limited to our proposed directions. First, we give two problems. First, how to ensure that the channel model intelligently adapts to the actual environment. Second, how to build a multiple level cascaded channel model. Consider from two aspects. First, changing or adjusting the parameters in the existing channel model through intelligent algorithms. Second, study more general cascaded channels. There are two methods for sensing and learning. The first is a fully intelligent deep reinforcement learning algorithm, which conducts sensing and training online and acquires channel data while learning network parameters. The channel data is enabled, and these data are used as the input of the network to obtain the parameter data in the channel model. At the same time, we need to consider the cascaded channels of multiple level connections. In emergency wireless communications, the transmitted channel experiences air feeding, mainly affected by weather factors. That experiences ground and on-ground feeding, earthquake and other buried pressure scenarios. And finally, reaches the receiver. It may be forwarded through many base stations or released in the middle. At this time, we need to introduce more channel parameters into the existing channel model, hoping that these channel parameters can characterize the real impact of existing disaster scenarios. Also at the same time, for the cascaded channel, the correlation of the signals need to be considered, and it is hoped that we have a simple form that can be used to clearly construct the cascaded and represent the cascaded channel model. In the accident area, UAV ad hoc networks, wireless local area networks, cellular mobile networks, and wireless sensor networks in the Mohan-based EchoLets provide a variety of transmission mechanisms, network access protocols, and user terminals for rapid rescue. Besides, seamless information exchange and effective cooperation among various entities are vital for rescuing in accident areas. However, the end-to-end network latency from the front line to the command center is constrained by the high mobility of rescuer, congested interrupted base station. The trajectory of UAV, the location of survival, the data transmission between different interfaces. Therefore, the coexistence of heterogeneous network, we call that HEATnet, with sharing resources are very challenging for low latency. As an effective solution for seamless and ubiquitous connectivity, SATCOM has been widely concerned in the emerging 6G technologies. However, there are large amounts of access devices with various transmission modes corresponding to heterogeneous networks in the SATCOM systems. For emerging scenarios, the burst service flows generated by various equipments are required to communicate at a critical delay requirement under the heterogeneous networks, where the inter-network handoff frequently happens based on the instantaneous channel condition. Therefore, the heterogeneous networks integration is an urgent issue to be solved in emergency wireless communications. After disasters, many rescue missions demand real-time decision-making and perception, such as sensing, data dissemination, and map construction, which highly rely on effective data collection and processing, availability of low-latency computation. Mobile edge computing can provide a sufficient computing resource for computation-intensive tasks. We consider a post-disaster scenario that sensors is placed to collect real-time sensing information, and the mobile edge computing node is placed to provide more computing resources. Here, the intelligence of the emergency wireless communication system is embodied in two aspects. First, the channel between the sensors and the mobile edge computing node experience similarly feeding and shadowing under the post-disaster scenario. So the risk-equipped UAV is used to improve the propagation induced impairments. Some papers show that RIS can reduce task latency and achieve high energy efficiency on the mobile edge computing. Second, edge intelligence, which refers to the deployment of machine learning algorithm at the network edge, can facilitate urgent decision making for rescuers. For the RIS, okay, one of the most typical application scenario of RIS is to assist the transmission of users who are static or moving slowly. In this case, the duration of one channel coherence block is usually tens of milliseconds, which is much larger than the time duration for adjusting the RIS. Most of existing research contributions assume that the RIS reflection coefficients can be only adjusted once for each channel coherence duration. However, one of the most typical application scenarios of RIS is to assist the transmission of the users who are static or moving slowly. In this case, the duration of one channel coherence block is usually tens of milliseconds, which is much larger than the time duration for adjusting the RIS. Therefore, adjusting RIS multiple times in one channel coherence duration, namely the dynamic RIS configuration, is practically valid. This unique characteristic opens up new research optimistics such as dynamic passive beamforming and resource allocation schemes, which merit further investigations. Okay, for the MI, the first part of intelligent MITT communications are intelligent reconfigurable coin arrays and reconfigurable metasurfaces. The system model of intelligent reconfigurable coin arrays are shown in the left-hand side. The photo of intelligent reconfigurable coin is shown in the right-hand side. Each intelligent coin has multiple intelligent units. The intelligent units are also shown in the right-hand side. The magnetic field can be flexibly concentrated to the receivers according to their locations or requirements using the intelligent reconfigurable coins. The system model of intelligent metasurface is shown in the left-hand side. It can be observed that the magnetic field generated from transmitter are passively concentrated. The circuit of each unit is shown on the right-hand side. The intelligent metasurface can be combined with intelligent reconfigurable coins to make hybrid beamforming, as we show on the right-hand side. The second part of intelligent MITT communications is the intelligent route for MITT waveguide. If the underground users are far from the ground, MITT waveform needs to be used. Thus, it is important to investigate the route scheme. The first problem is what's the optimal routing scheme for MITT wave? How to find it? Also, the occurrence of natural disasters may cause the underground relay to be destroyed. The second problem is what kind of routing scheme has the optimal robustness. The third part of intelligent MITT communication is the intelligent wireless-powered MITT network. An intelligent wireless-powered MITT network is shown on the left-hand side. In post-disaster underground areas, it is very difficult to replace batteries or charge the devices for underground users. To guarantee the sustainability of MITT network, it is important to wirelessly charging the underground devices while communicating with them. It's also important to find the optimal resource allocation scheme for this kind of network. For diverse quality guarantees in intelligent emergency wireless communications, mobile applications provide different text message, video, and picture sharing applications, and social media networking mainly force this. An emergency call placed by a smartphone with such capabilities can potentially increase the chances of a successful emergency response by providing, along with the multi-medium call, precise location information. Thus, heterogeneous services exist in emergency wireless communication networks under complex disaster environment, such as signaling with strict delay, data with loose delay, voice with tolerable delay. Emergency wireless networks are envisioned to support an uh, uh, amalgam of diverse applications and services with heterogeneous performance requirements. Besides, because the service and the wireless channel conditions are diverse and highly dynamic, diverse quality of service guarantees are difficult to be satisfied. As a result, new architecture and framework are needed to effectively support intelligent, diverse quality of service guarantees in real-time traffic transmission in heterogeneous emergency wireless communication networks. And the corresponding resource allocation schemes are required to optimize the performance of the quality of service to constitute a powerful tool for coordinating communication among citizens, call centers, and first responders. First, let me introduce three powerful tools to achieve larger capacity and high spectrum efficiency under the heterogeneous delay guarantee in emergency wireless communications. A delay bounded quality of service exponent, effective bandwidth, and effective capacity. Delay bound quality of service exponent builds up the relationship between the queuing length threshold and the probability of queuing length exiting the given threshold. As delay bound quality of service exponent increases, effective bandwidth increases while effective capacity decreases, which means the higher minimum service rate is required and the small maximum arrival rate can be supported. We propose and analyze the QoS-driven optimal power allocation scheme for single statistical QoS provisioning, which aim at maximizing the system's throughput subject to a given delay quality of service constraint. It can be seen from figure that the delay QoS constraint gets very loose, the optimal power allocation converges to the water filling scheme. When the delay quality of service constraint becomes very stringent, the optimal power allocation scheme is reduced to the channel inverse scheme. However, in emergency wireless networks with various kinds of service, if all links in the wireless networks have the joint power constraint, the statistical delay bounded QoS provisioning needs to be jointly considered for all links at the same time. Under this circumstance, the transmitter needs to satisfy different delay bound QoS requirements under the joint power stringent simultaneously. We call this kind of technique the heterogeneous statistical delay boundary QoS provisioning. To solve this problem, we can build the aggregated effective capacity model for the emergency wireless transmissions with heterogeneous statistical delay boundary QoS provisioning. This is also an expected meaningful research direction. Okay, having said so much, we are approaching the end of this tutorial. Previous work have given some useful scheme for emergency wireless communications. However, how to achieve intelligent, completely achieve or comprehensively achieve intelligent emergency wireless communications is still a very challenging and difficult problem.